this looks like as if I'm giving you a progress report of my 35 years of a career. But that's not the right idea. The right idea was that I'm going to tell you why we need to concern ourselves with mechanical performance of polymers, because that's what we're all concerned about, meaning several 100 billion pounds of polymers are chiefly used for mechanical purposes alone. And their strengths, whether they break, is of course the whole deal. So in order to describe how they break, it turns out I have to tell you how they bounce. In other words, why we treat them as an elastic body. And furthermore, in processing, you try to cause them to flow, and there's a transition between elastic and being able to flow. So this is why there are three parts to it. I realize it's an extremely ambitious title and presentation to tell you everything from fracture mechanics to melt rheology. So I will use first half, just relax as if it was just some storytelling introduction for the first half, to pave the road to discuss what I'm excited about, nothing published on the fracture mechanics of polymers, where I think we start to see a different light, very different light on this massive subject of 100 years old fracture mechanics. We're using polymer as a type of material, but the implications of our finding will be applicable for other materials. So in any case, the only way you can avoid giving a good talk is you're running out of time. And I'm going to run out of time pretty soon. So I will try to reserve half of the time on this unpublished part, which I'm very excited about. Anything you worked out, you kind of say, hey, that's no longer interesting. But as I said, to be able to explain this. So in any case, obviously, I'm not boring you with this chain of structural property relationship, plus the fact when you process, you can change the structure is the whole game. I see there was a problem in the beginning. It has it again. It freezes in terms of me moving. So let's see if it does this again. Okay, now it works. So there's a melt state. You need to process it. And depending on how you cool it, depending on material, it may be glassy or semi-crystalline. The processing can affect the structure. So that way, if you can improve the structure, you may have a chance to develop better property. But the property is the most difficult because that's the effect you're seeing. You don't know what is the cause. You have to trace back in this inverse problem and 6th order magnitude. So in any case, I'm proud to tell you that we have been continuously supported by NSF in the last 18 years or so. And we're excited to embark on the last episode. So I'm sharing with you a story of the Sega that really says there are 3 episodes. So in any case, we do science like this. We have a puzzle. You guys probably have it. It could consume you a whole afternoon. You won't be able to solve it. Because when you put up the rest of the 5, you find it's mismatched. It's not right. But my wife told me there is a solution, and the solution is different. You see, these 2 butterflies are facing to each other instead of in the same way. What does this tell you? Don't be a frog looking into the sky. You have a very limited view, and that view can be entirely wrong. So again, I probably only need to go this slide and I can finish my talk already. So basically, in my world of polymer physics, it's about understanding the melt rheology first. And we wrote a book about it. It's about understanding why this thing behaves solid-like. And then when you cool down, there are questions about, gee, why glass, now I see it, why glass can yield at all? And then if it's semi-crystalline, there is a question of actually, you want to avoid crystallization destroying the chain entanglement. So how to do that? And lastly, moving to fracture mechanics, there's the issue of how to understand the science of fracture mechanics, having to do with answering questions like toughness, why it's a constant. So this involves 3 generations of students. I'm sorry, I don't have a lot more time to describe this, everyone. So basically, there are 3 generations color-coded for each of the topic. This is a summary slide. So if you look, our material, of course, are of 3 types. There's rubber, there's thermoset, there's plastic. So I'm going to say a little bit about in the nonlinear region, how we think about glass breaking at the molecular level, and eventually answering the question of where fracture mechanics fits in this breaking. And it turns out when you establish that basic notion through fracture mechanics, there are a lot of gaps to fill in each of these areas. So I will quickly run out of time, so I need to be quick on each of the first two topics. The first is already after this book, these Bibles, we begin to learn from phenomenology that these liquids break apart. They break apart in a non-uniform way. And I have a summary lecture on this topic, summarizing this book, and I also have a free copy of all the lectures in a 3-credit course that I made it available on YouTube. And it starts to address all the conclusions regarding the whole set of phenomenology that was unknown to us, and we have subsequently have a coherent molecular picture about why these things happen. So I'm just sharing that with you, and I'm just going to remind people who are not or who forgot your polymer science, the key part about polymer for us is the fact polystyrene is very thick, polyethylene is very thin. And that's depicted by something called packing length, where Professor Witten knows so well. And you popularized that concept, basically. It was discovered in the 80s. And this is a second most important parameter besides cone length regarding polymer. And I discovered by looking at dozens of polymers, your cone length actually is quite narrow distributed. This packing length varies a great deal. It's an important parameter. Well, I may not even have time to go into detail. So in any case, I'm just flashing through, enjoy this as a story about the first episode where this kind of movie first caused us to drop our chins, really, realizing that the sample actually is breaking apart. This is about 1 millimeter. So it's breaking apart in my language, of course, having to do with something molecular happening. So we, of course, worked over more than half a decade to figure out the science behind it. So this is just an impression. And then, as I said, there are a lot of information about it. The most surprising thing was even if you make a step strap, in other words, you just, H is the height, you make 3 H's to the right, you wait a little bit, at some point, it will start to break. This is a piece of polymer melt. Look, it started to break. I know, a laser, yeah, so it started to break here. So we predict that the same breaking will happen in extension. So you make a step stretching. Oh, you wouldn't let me do that. Make a step stretching, you wait a little bit, this filament breaks apart. Elastically breaking apart. Let's save the time, let's not wait for its breaking. So basically there is the need to conceptualize this and to rationalize this with a simple model that's way beyond what a tube model can capture. I see this movie is not the one that's working, but basically there is an issue of forcing balance. You cannot stretch the chain beyond a certain level. The chain will have so much tension in it, it will start to retract. So that's the failure of your solid. And then let's move on to this more fascinating, more difficult problem of glass. So there are books written on this. There are tons of books written on this. And the key question was something like this IR movie shows. This is a piece of polymer. If I don't tell you that this is deeply glassy, you wouldn't know. If it draws as if it's a piece of liquid. It turns out this is a polycarbonate 100 degree, more than 100 degrees below TG, yet it yields. And the summary of this topic is really that we think the chain network through uncrossability was what enabled this. So I'm going to go very quickly through this idea of, or work out what happens here. So in this episode 2, of course, you have amorphous, that's easier. And then you may have semi-crystalline that makes life even harder because the semi-crystalline could either be glassy or rubbery, depending on TG. So, a little bit of a boring review. For melts, we handled the chemistry we can specify, and I just treat this as a network, and not to worry about the specific chemistry. As we cool, what happens? Well, what happens is obvious. That network is still there. Of course, we haven't done anything. We just quenched it, or it just cooled down. But moreover, the way we did in rheology is we parameterize it. All the specific details are in some phenomenological parameter like the friction, so that all polymer to us is less like this picture of a rice noodle. All the chemistry can be dealt with. In glassy state, can we also parameterize it? Well, the short answer is yes. The only thing is, in addition to treating the structure of this network, there is this additional structure, which I call the primary structure, because of vitrification. So you have to deal with the fact that they are sitting a landscape, all that. And then in polymer, you have how long it is, become entangled, and then, of course, elasticity arising from the fact you have sufficient entanglement. In the polymer, in the glassy state, you deal with the same structural problem of how to depict the density of the network. It turns out that density, of course, is a fraction of what in the limit of fully. So basically, there are details I'm omitting about how to think about the structure. But let me continue by saying that the whole game of glassy polymer is about understanding the fact there is a brittle ductile transition. And it's affected by 5 parameters I listed here. I will run out of time, so I will be very quick on this in terms of what each parameter does in terms of whether it affects the primary structure or it affects the chain structure. One of the magician effect is the so-called rejuvenation. You pass your polymer through this cold two-row mill, then this very brittle polymer turns ductile. So that's like no chemistry change, it turns ductile, right? So that's called rejuvenation, one of the effects. Secondly, if you have stop this so that's not. Secondly, if you have this polystyrene, it's typically brittle, but after melt stretching, it turns completely ductile. Okay, so these are the effects. And for me, this allows me to introduce a concept which I kind of own it because it's a concept that's well known, supposedly. Basically, there's geometric condensation of the chain network. So if I stretch in the Z direction, and then I look head on, I find my load-bearing strands condense. It's the same cross-section area that's shrinking, but I still have the same number of load-bearing strands. And in fact, the limit of that is fiber. This is why fiber is strong, because every area is effectively bearing the load. In other words, prior to that, this network is very sparse, it's very loose. So the picture for us to proceed to understand why some glassy polymer can be ductile is these load-bearing strands of my stretch globally. Keep in mind, my sample will involve a million of such units, millions. But these load-bearing strands, as I stretch from one end to the other end, 1 million away, they will start displaced. When they get displaced, the neighbor will eventually start to move around. So you can create some activation zones, if you like. And that grows as you stretch more and more. So the brittle ductile transition, in my mind, was a Goldilocks temperature above which the network survives and activates, below which the network falls apart, and therefore, of course, you cannot achieve activation. And there's no mobility available for you to match with the imposed rate. Therefore, it breaks apart. So basically, this allows us to understand why melt stretching make polystyrene ductile, something known for 50 years, because you bring the load-bearing chains closer, so your activation zone only need to be smaller and achieve activation. And you can understand physical aging and rejuvenation in the same manner in terms of how how dormant the system is. So basically, we can understand it. So if you allow me to say, from this, I can even imagine how to calculate the stress. It will be just the load-bearing chains and the area density of load-bearing chains. And this gives me a notion of what would be the theoretical strength of my polymer provided by these two parameters. So if you fit this model to the experimental data, you find it offers some support of this idea of the fact that the strength of your material is dictated by the tension available in the chain before the network falls apart. And the way it falls apart mostly is through chain pull-out. So in any case, we have some idea about how much strength there is in a polymer. So I will quickly go through the semi-crystalline polymer. The story there is very simple. We are lucky to have something like polyethylene and polypropylene. They have such good properties because they crystallize so fast. Once they crystallize so fast, they can preserve the chain network. That's my conclusion on this topic. So in this world of sustainability, we have biopolymers or biodegradable polymer that's just poorly brittle, such as PLA. It's just horrible. And but is there a way to make it so I have some samples. So either you can make it crystalline or not crystalline, but in both cases, they are brittle like crazy. Okay, so both both are brittle, either glassy or semi, or either amorphous or semi-crystalline. So I play the game of rheology. I stretch this polymer in the melt state, hoping that I stretch it still in the elastic limit. So strands are all lined up to induce crystallization at each mesh size.
But I have something else.
So that I have enough nucleation of crystals, and each crystal is confined to the mesh size level because there's only that much available material. So you have a nano confined crystallizing PLA that's tough, transparent, and heat resistant. That's boiling water. So that's the world first PLA cup of such property. So this is a great example of PSP, meaning processing leads to better structure leads to incredibly better property, because we successfully inverted this problem. We know what structure is required for the property. So with that, I think I'm hitting the mid mark. I'm perfectly on time. So this is the introduction. All that have been published. May take time for it to catch on, but I move on because I cannot wait. The knowledge, the understanding, the experience we have had in the first two episodes really allowed us to ask some fresh questions for this fracture mechanics. It's a vast subject, fracture mechanics. We never touched that subject. It's something we shy away until we see that it seems like we can make a contribution there. And this third episode is what I should spend my bulk time, the next 20 minutes maybe or so on. But it's all summarized here already. So I think for the first time, we were identifying the science behind it. In the sense, we are going to address the question of, gee, where does fracture mechanics come in? Why it works or not for polymers? Therefore, we are able to answer the question of whether polymers are flaw tolerant or not. And more importantly, why toughness is a constant or what determines magnitude. So this is a topic. I tell you this topic is very contemporary because this is a paper, I'm not going to disclose it. This is a paper of last year, still telling us that polymer is flaw intolerant. That the breaking of polymer is because there are flaws. Okay, this is last year, so it's contemporary. And is this so? Is the question. So if you open textbooks, they will blame, look, I highlighted, they will blame all this is just flaws. Polystyrene breaks, right? This PRA breaks is because they are flaws. Is that so? And so you can flip another page, it says same. Basically, there are flaws as we know it. And there was some confusion about what to do with it. So let me just review for you fracture mechanics using 2 minutes of your time. This is fracture mechanics. It started with people dealing with window glass. It's very brittle. And it breaks at 100 megapascals. And it's two order magnitude smaller than the so-called theoretical strength of 10 gigapascals. Man, how do I deal with that problem? So people figure out since English that there must be some defects in there. And if you follow that logic, your window glass must have flaws on the order of 1 microns. Okay, so here's fracture mechanics. The next minute is the whole 9 yards of fracture mechanics. When English first did a theoretical calculation, dig a hole of this plate, and he found the stress would diverge. Okay, so the stress would diverge. Lord, what happened? Yeah, the stress would diverge if this aspect ratio become infinitely large. And people said, people are very much annoyed by this. Because in that limit, infinitely small load will give you fracture by definition. Very annoying. And that didn't happen. So this argument must be abandoned for the moment, let's say. So that's where Griffiths moved on. Says Griffiths is 1921, many years later. He used this solution and says, let's consider something different. Take a piece, unload, without a cut, without anything, intentional cut. You draw it. In the elastic limit, you store energy, of course. And then you make a cut. What happens? You must release energy because that cut made sure you no longer store as much energy anymore. So the difference is what you release, the energy. That's this term. You can do a scaling argument to find out what it should be. Now, his question was to ask, once you have this cut, can it grow? He says, let me just have a little more cut. I will release a little more energy. And let me compare that energy with what's required, which is surface tension. The energy required to create new surface. He says, oh, if this is greater than gamma, it must fracture. So you no longer need to shy away from fracture mechanics. That's all of the fracture mechanics, linear elastic fracture mechanics. That's all there is. And with that, it leads to the famous law, right? You all know that's Griffiths. Oh, that's not the whole point. Remember, we call this pillar 1. There's still this pillar 2. In other words, Westergaard further established that you can calculate and find how the stress even changes as you move away from the tip, not just the solution at the tip. And he found it's going to diverge. You meet the same problem. The stress is going to diverge. It's nasty. We don't know what to deal with it. Thanks God. So what to do? I close my eyes. I says, if I load, which is this K parameter, so-called, if I load, at some point it's going to break. I close my eyes, says, okay, so it just means my load need to reach a critical value called a C. So which means K need to reach a value C. And it turns out you can prove that K is related to G. So all of a sudden, you realize I can abandon pillar 1, everything converges back to pillar 1. Abandon pillar 2, everything converges back to pillar 1. Everything is energy argument. That would work. And this is the first time people learn about it from glass and metals and apply to polymers. These are 2 papers. The first 2 papers are on elastomer on the left and plastic on the right. What happens? Well, bad news happened. Bad news, which alarmed me and I got crazy a year ago when I learned this. Bad news. What you learn is that this GC, the energy thing, is thousands of times larger than surface tension instead of equal. Only when you equal this energy argument works, right? It says, I need to pay this much. It turns out I give 10 times, 1,000 times before it would break. So this argument no longer is effective, at least. Yet it still works. The GC is still constant. In other words, depending on different cut, I still have the load being square root of A. So that's where the mystery is. And we are in the middle of solving that mystery. So basically, you find it doesn't matter for your elastomers or for your plastics, both cases, they are orders of 2 order magnitude larger. Here's the textbook. They recognize that. This is one of the textbooks says, oh, by the way, I know the GC is much smaller. GC is much larger than gamma. This is the fact. And in fact, this difficulty was just ignored. Okay, I still need to preserve it. So what happens? Okay, you must have just plenty of plastic dissipation going on that you didn't take it into account. In any case, the origin of this is all this, that the theoretical strength being much smaller than experimental strength. And that carries to elastomers as well. Theoretical strength being much smaller than experimental strength. I'm going to review this part as well. And then people find the same thing, that the toughness called GC is much smaller, is much greater than surface tension. So this becomes a paradox. On the top, the theory is bigger than experiment. On the bottom, for toughness, it's the reverse. So the textbook even called this a paradox in this book. It turns out, say the least, your theoretical estimate is wrong. So we actually, our episode 2 enabled us to answer that this is wrong, this type of guidance. The theoretical strength of your polymer is only 50 megapascals, not gigapascals. Same is true for the rubber. The theoretical estimate is wrong because not all the bonds bear the load at the same time and break at the same time. It does it in stepwise manner in such a way that explains that such discrepancy shouldn't exist. What about this discrepancy? Oh, here's the problem now. This discrepancy means, hey, should I develop a theory to take into account of plastic effects? Or should I develop a better theory that does something better? Or we need to even completely update our understanding on this topic. So through this question to you, this is almost the core question of the whole thing. You got what you observed as energy being much higher, that you have to pay is much higher than you have to just pay to create the surface. Therefore, to me, this energy argument no longer valid, meaning it doesn't give me insight anymore. Gamma does not prescribe the magnitude. But then why this thing is still constant? So that this is true, actually. And what determines the magnitude of this? This is the last questions of this. I want to indicate fracture mechanics is a tremendous success because they identify what is GC. They could somehow care less, or in fact, unable to answer why GC is constant. When the energy argument doesn't work, you cannot answer why GC is constant. And you cannot, certainly cannot answer why it has the magnitude it does. So we're just start to scratch the surface of this. We just discovered that there could be issues here to be looked at. So this is a map for us. So today I'm just going to give you 2 examples of amorphous glass versus a elastomer in terms of the fracture behavior in light of all these questions that I raised. So the rest, relax, it's just data now. Motivation is done. It's data. We're going to try to read the stress at the tip because I'm a believer that the fracture occurred because the stress at the tip exceeded the inherent strength. In other words, it's a stress argument rather than energy argument per se. So let's see how far it goes with this. So which means you get to one with card, one without card, and you do birefringence, which is a good way to at least have some indication of the correlation between, see, this is a white line with crossbar risers, So I have two different samples. The other one with a cut already. So showing that I can at least keep track of the molecular deformation that's taking place. And in the case of uncut, it correlates with the stress that occurs. In the case of ductile material, you see that PET at the left, at the right figure, it doesn't go brittle failure, it necks and yields. And better yet, if you have very birefringent materials, you don't use white light, you use monochromatic light, just count the number of fringes as it turns black and white, black and white. For the white light, you have this Michael-Levy chart to guide you about how the birefringent builds up. So here's our first result. PMMA with a cut, with white light. So as the color changes, it shows the birefringent progresses. So this is the raw data, and you can analyze it. So my student tried to take a still picture of each, blow it up. So the 4K video helps because we need to resolve what happens at the tip. And you can translate that color into a distance from the tip kind of information. You find, what do you find? What do you find? The stress or birefringent build up, but then plateaus. And you can quantify this information. The stress build up, because I plotted as 1 over R, square root 1 over R inverse. So tip toward the tip is this way. It builds and then levels off. And it levels off at, I pray to God, meaning indeed we did probably, that it levels off at a scale that we can resolve. 50 microns, 100 microns. Let me just inject this information. You do exactly the same for window glass. This cutoff will be 1 nanometer. Impossible to resolve. But for polymer, it was resolvable. And quite interesting, it's very different from traditional fracture mechanics. The tip stress builds as I load more and more. Linearly, tip stress grows with the loading parameter, the so-called stress intensification factor, linearly. If it's linearly, that slope, as question mark, just by dimension analysis, that slope involves a length scale, this slope. The tip stress build up linearly. This is just nothing but normalized loading parameter involving the cut size. If you have different cut size, you can all collapse the data there. And in more detail, so you can do a different cut length, same loading parameter. So what happens is this linearity holds all the way to the point of breaking. As I said, this linearity means that a length scale pops out. It just pops out. And that length scale is about a fraction of a millimeter, a tenth of a millimeter. So not only that, this relationship works all the way to the point of fracture. Oh my God, that allows me to say a great deal. In other words, I carry this relationship all the way to the fracture. Therefore, I carry the way all the way to Kc, which is the toughness thing. I realize that is related to the tip stress reaching some limiting value, which we identify as inherent strength. So all of a sudden, Kc not only has this operational definition of the loading and cut size, independently, I have Kc related to the inherent strength of your material and a characteristic landscape. I answered 2 questions in this already. Why K is a constant, Kc is constant? Because inherent strength, of course, is a constant. The only thing left is why you have this characteristic length scale that's constant. Separately, this expression already said what is the magnitude. It's sigma times p square root. So here's a review. I want to impress you on this point. On the left is what we know as fracture mechanics. Okay, what we only have is this operational definition. Okay, it does, of course, that reaches some critical value, but it doesn't say anything about what is this Kc. It just have an operating definition. In other words, you go to an experiment, you go to a lab, you can tell me what is Kc, but I cannot tell you what it determined by and why it is constant. And similarly, because of this relationship, you can get GC. What is the new? The new part of this is that it's actually related to the inherent strength and the characteristic parameter. And if you plug this way, you find it's again involving this. Now it's linear because they are squared. It's involving a length scale and work density of fracture. So we answer both questions of being constant and magnitude. So I know I'm running out of time soon, and just relax. And this is just a second part on elastomers. We want to find out whether similar things occurs. And elastomers, the way we had it, it was very barrier-friendly, so we use monochromatic light so that there is plenty of orders to deal with. So this is the tip. You use a sodium light, and the tips start to build one order after another. So if you're patient, you'll see that setup is similar, except we use the. I was just proposing before coming that we're going to use laser to do it too, because we are just looking at the last millimeter at the tip, just the last millimeter tip. So the scale, I didn't give you the scale, but roughly speaking, a millimeter is probably something this big. Yeah, sorry, it doesn't speed up. Yeah, so you will see some more. So yeah, here is basically carried through. Do the same thing. Yeah, so the key point is the same. It's boring, right? So it's just like plastics. The stress stops building. In other words, you show a big kink around a scale, it's just manageable, 50 microns to 100 microns range. Okay, and again, this tip stress keep building. You see, without this plateau, the last point is at the infinity because it's inverse. Without this plateau, I wouldn't be able to confidently tell you what is the tip stress. So this is the key. If this thing keep going, then go ahead and resolve it because it will go forever. That's the window glass. You can never do this experiment. Can never resolve below wavelengths of light. So with this, we find this again, it's linear. That slope, 160 microns. So if I review it for you again, fracture mechanics told us for our polymers, okay, window glass definitely is flaw, intolerant. In other words, it cannot tolerate flaws. But does this really work for our polymers? Well, the framework of a linear fracture elastified is to say, give me an uncut sample. The way I understand the fracture strength is because there are flaws. Okay, period. And how do I estimate this? I better get GC. How do I get GC? I use a cut. I use the cut if you go to pillar 2, you met the trouble that Irving was trying to persuade us to think about, because this thing will diverge, and he just say, oh, there must be a messy zone, so-called, a damage zone. There's so many words for it. So there's something going on that somehow stop the singularity from going to infinity. And then the rest I can close my eyes, because this just keep building, it's saturated to this level, and there's a magic point, boom, fracture occurs, and then we go to GC. And once we go to GC, then of course we go back to energy argument. For polymers, it's pretty clear our conclusion. When you have no cut, the strength is merely, roughly speaking, revealing the inherent strength. Fracture mechanics is not in the business, per se. 50 microns, 100 microns. So you just need your sample to be clean, not to have flaws of a millimeter, which we don't. Pre-cut, the scenario is so different. The tip stress builds up. Oops, this thing actually flips the, yeah. The tip stress builds up, not this scenario. But I want to remind you, if you are not able to resolve, you see, if your maximum resolution is here, you won't be able to differentiate this result from that result. So the existence of the saturation that's resolvable is key. I will actually not go through too much with you. There's another scenario. I showed you a single cut. There's another scenario called pure shear. This actually was the one driving me crazy, because this one, it was so cleverly derived as a protocol. Basically, it says GC should be given by the work density times H. If my H is bigger, I have a bigger sample. So my work density only need to be lower because this left is constant. I was so mad with this result because this is truly a beautiful way to say it's energy argument, right? What happens if I have you on the next slide? So basically this is what happens. What happens is you prepare this. You prepare a sample that's taller versus shorter, okay? Okay? And what is said was that the taller one will break much earlier because we have so much more volume to store the energy, right? Okay, and I was so mad with this result, with this argument. But look at what happened. At the same load, the taller one simply has much more intensified stress at the tip. You follow me, you guys? Of course, then it breaks early because, you know, so the rest, I think, yeah, maybe it takes more than a minute for you to absorb, but that's what happens. So this is a different ages. At the same load, the taller one intensifies, have much more stress at the tip than the shorter one. So it turns out, this H magically comes into the tip stress such that this product has no stress H dependence anymore for the GC. So I know I'm running a little fast, but believe me, the end story is this load parameter become a function of the height, because that's the only length scale left. The cut is so large, the width is so large, the only length scale is the height. So in fact, it's inescapable. It's a cheap solution story because this thing has to, you're missing a length scale. So it's quite trivial in that sense. But the reality is this, as I predicted, it breaks involving the same, sorry. Did I do it? Oh God. That's the happy news of it. It breaks at the same tip stress, at the same intensity of stress, involving different load levels, and you can collapse the data and so on and so forth. I'm done. So I think I managed my time relatively okay. So yeah, so this is the whole summary. It summarized all the 3 episodes. It's quite a journey. You have the first episode talking about something really shocking. I was somehow known as the shear banding guy, but we moved on, right? So this shear banding was indeed very important. It did tell us, Jesus Christ, even in liquid state, the structure can break apart. Not only break apart, they break apart inhomogeneously. And then the glassy problem is really a difficult one. Really a difficult one. Because iron idea doesn't work. Iron says, give me stress, the barrier will always be lowered. Then if you follow that argument, your polymer will never be brittle. You can always yield. So it turns out the structure is what give you the stress so that you can yield. If your structure, which is the chain network, breaks apart, then you cannot yield. That's my theory for the brittle ductile problem. And then this is just, of course, a beautiful example of showing processing structure and property relationship. And lately we found, since you are talking about breaking, we better just have an intentional cut and find out the physics of the breaking. And in particular, answer the question of when you have no cut, whether the breaking has anything to do with the business of fracture mechanics. In other words, whether your material is flaw intolerant or tolerant. And we answered some of the elementary questions. So that's why it's constant, and that's what is the magnitude. What's left? What's left is we have no clue why P is 50 microns for polymers. We only feel lucky it was so big that we can resolve it. This answers many of the questions that why GC is 1,000 times larger than surface tension. It involves a scale that's not even molecular or microscopic. It's a mesoscopic scale. It involves a massive amount of energy. It was involved in the fracture, basically. With that, I close. Thank you.